everyone, this video will be covering OCR A-Level Chemistry A, Paper 3 from June 2024. If you do find this video useful, please do give it a like and subscribe. Question 1 is about acids, bases and salts. What is the pH of 1 decimeter cubed of 0.4 moles per decimeter cubed sodium hydroxide at 298 Kelvin? Now, as this is a strong base, it requires the Kw expression that you rearrange to find H+ ions. So that would be Kw. The exact value should be in the datasheet, divided by the concentration of the hydroxide, which is just the sodium hydroxide. And that's equal to 2.5 times 10 to the negative 14. Then you'd plug this into the pH equation, so that's negative log of 2.5 times 10 to the negative 14, and that comes out to be 13.6. Part B is water is added to 10 centimeters cubed of 0.75 moles per decimeter cubed hydrochloric acid to produce 100 centimeters cubed of diluted acid. What is the pH of the diluted acid? Give your answer to 2 decimal places. Now, there's a range of approaches you could use for this, such as like working out the dilution factor or the C1V1 equation, or easier yet is to see that this is a 10-fold dilution. Therefore, the new concentration would have to be a factor of 10 less. So 0.075 is the new concentration. Then you plug this new concentration into the pH equation, and the answer comes out to be 1.12. Part C is a solution has concentrations of 0.3 moles per decimeter cubed ethanoic acid and 0.1 mole per decimeter cubed sodium ethanoate. Ka has been provided. What is the pH of the solution at 298 Kelvin? Give your answer to 2 decimal places. So we know that this is a buffer because it's made up of a weak acid and its conjugate base. So when you're using the Ka expression, you're using the normal entire Ka expression and not the H+ squared one. So from this expression, we need to rearrange it to find H+ ion concentration. So that becomes Ka, 1.75 times 10 to the negative 5, multiplied by the concentration of Ha, so the acid, that's 0.3, divided by the concentration of A-. So A- comes from the dissociation of the salt, which is sodium ethanoate, so that's just 0.1. That's equal to 5.25 times 10 to the negative 5. And again, to put this in the pH expression, the answer comes out to be 4.28. Then part D is a student is provided with hydrated copper 2 nitrate. The student needs to prepare a standard solution of copper 2 nitrate with a concentration of 0.2 moles per decimeter cubed. The student has access to the usual laboratory apparatus and equipment. Describe how the student would prepare 100 centimeters cubed of the solution, giving quantities, apparatus, and method. So let's start with the quantities first. Now we know the concentration required and the volume of the solution. So we can find out its moles, and by doing that, we can find out the mass of the solid required to be dissolved. So to start with the moles of copper 2 nitrate, so the moles of the salt, that would be concentration multiplied by volume. So that's 0.02 moles. And then to find the mass of that salt, it is the moles multiplied by the molar mass of the copper 2 nitrate, including the water of crystallization. So that is 241.5. So the mass required is 4.83 grams. As for the method, well, the first step would be to dissolve this solid, dissolve the solid in distilled water, and this would be in a beaker. Now, when you're doing this, you want to use a volume of water that is less than 100 centimeters cubed, because what would happen is you'd have to transfer this to a volumetric flask, which would be the next point. Transfer to a volumetric flask. And you'd also want to include the washings. So this is when you add water to the beaker that you dissolve the solid in and rinse it around, and also add this to the volumetric flask. And this is so that you don't leave behind any residue and you actually make the desired concentration. And then finally, you make up to 100 centimeters cubed. So hopefully you now see why when you first dissolve it, you can't use 100, because eventually you'd have to make it up to 100, not to mention you're also including the washings. So make up to 100 centimeters cubed and invert the flask, that is, to mix it. Right, so that's 5 marks. It's 2 marks for the calculation, and the other 3 marks are bullet pointed over here to make it up to the 5. Question 2 then is about different areas of chemistry. hydrogen gas is manufactured by the chemical industry from the reversible reaction of methane and steam as shown below. Why do all average bond enthalpies have a positive value? That's because bond breaking, which is what bond enthalpies are referring to, bond breaking requires energy, so that means it's endothermic. Bond breaking is endothermic. Part 2 is to determine the carbon-hydrogen bond enthalpy in kilojoules per mole using the information above. So this is the delta H equation, which is equal to the bonds broken subtracted from the bonds made. So for delta H, we have been provided with that, 195. That's equal to the bonds broken, so that's 4 CH bonds broken, so 4 times X, plus H2O, so that's 2 OH bonds in one molecule, so that's 2 times 464, and subtracted by the bonds made. That looks to be 3 hydrogen bonds and 1 carbon-oxygen bond. Right, so then to simplify that, that's 195 equal to 4x minus 1457. Then if you rearrange for x, that's equal to 1652 divided by 4, which is 413. So that's positive 413. Now you don't quite need the positive sign because we've already established that bond enthalpy is positive. You can just leave that out. So just 413. Part 3 is hydrogen gas is being considered as a household fuel to replace methane. The enthalpy change of formation for water is minus 285.8 kilojoules per mole. Determine the energy released when 60 meters cubed of hydrogen is used as a household fuel at RTP. Give your answer to 3 significant figures and in standard form. So it seems like this energy value is the energy released for the formation of 1 mole of water, so I'm assuming that's made from 1 mole of hydrogen gas. Therefore, what you'd have to do is try to figure out how many moles of hydrogen are in 60 meters cubed, and then multiply that by 285 minus 285, as that would tell you the energy for that many moles of hydrogen, if that makes sense. So to start off with, the moles of hydrogen, and we can do this because we know it's RTP, so use the moles as equal to volume of gas divided by 24 decimeter cubed formula. So that's 60 multiplied by 1,000 to convert that to decimeters cubed, divided by 24 decimeters cubed. That's equal to 2,500 moles. So if we multiply this by the energy value, it tells us the energy released for 2,500 moles. So that's 2,500 times minus 285.5. That's equal to minus 714500. Now they want this to 3 significant figures and standard form. Therefore, that's 7.15 times 10 to the power of 5. Then in part B, compound A is a chloride of a period 3 element. A student carries out the 2 steps below to find the formula of compound A. In step 1, the student adds 5 times 10 to the minus 4 moles of compound A to water, and a colorless solution is formed. In step 2, the colorless solution reacts with exactly 60 centimeter cubed of 2.5 times 10 to the minus 2 moles per decimeter cubed silver nitrate to form a white precipitate. So we know the presence of chloride and silver ions together would produce AgCl as the white precipitate. Write the ionic equation with state symbols for this reaction. So that's silver ions that are aqueous, reacting with chloride ions, also aqueous, to form the precipitate, silver chloride, that's a solid. Part 2 is to determine the formula of compound A. Now, based on the information provided, we have what we need to calculate the moles of silver ions. And in doing so, we can figure out the moles of chloride ions because they're in the 1-to-1 ratio. So if we have the moles of chloride ions and the moles of compound A, we could divide both of them to see how many chlorides fit in compound A. And in doing so, we could figure out what period 3 element it's bonded to. So let's start with the moles of silver ions. So that is its concentration times volume. And that's equal to 1.5 times 10 to the minus 3 moles. Now that we have this, we know that this value is bigger than the moles of compound A, and you always do the bigger value divided by the smaller one. And that's to figure out how many chloride ions would be present in compound A. So that's 1.5 times 10 to the minus 3 divided by 5 times 10 to the negative 4. That's equal to 3. That means there are 3 chloride ions present in compound A. Now, if there's 3 chloride ions, that means the ion that it's attached to, the positive ion, has to have a +3 charge. So we're looking for a period 3 element that would form a +3 ion. So periodic table here, period 3. So in group 3 is aluminium. That means that this compound is AlCl3. Part C is compound B, shown below, is an antiviral medicine. What is the molecular formula of compound B? So as straightforward as this question looks to be, I know many a student that tends to mess it up because of hydrogens. So when it comes to calculating or counting the hydrogens, just try to be very careful. So let's get the easy elements out of the way first. So we know nitrogen and oxygen are easy because they're quite obvious. 3 nitrogens and it looks like 7 oxygens. Okay. Carbons are also easy because they're just the corners. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Now for hydrogens, which for some reason is always tricky, but we can go slow with that. So that's 1, 2. Now over here there's no hydrogens because carbon is forming the maximum number of bonds. So that's 1 double bond and then the 2 single bonds. So no hydrogens there. There would be a hydrogen here though, and 1 over here. So that's 3 and 4. Fifth one would be here, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, because both those corners over there are methyl groups, so there's 19 hydrogens. Part 2 is how many chiral carbon atoms are there in one molecule of compound B. Chiral carbons are carbons that have 4 different groups attached to it. So for example, if we look at, I believe this is one chiral carbon because the 4 groups attached. The first one is a hydroxide. The second group is a carbon that's bonded to a hydroxide. The other would be a carbon that's bonded to a nitrogen. And the last one is the hydrogen that would have been present over there. So 4 different groups around that blue carbon. So would it be similar for this one as well? So that's the second chiral carbon. Third one is this one, and it looks like the fourth one would be that. Is there anything else? Not that I can see. These carbons do not count because they're part of a double bond, so there's no 4 different groups, it would just be 3 groups, and that is not part of the criteria that we're looking for. So it seems like it's just 4 chiral carbons in this compound. Part 3 then is a research chemist synthesizes 2 related compounds, compound C and compound D, from compound B. In compound C, the nitrogen atoms in B have been replaced by phosphorus atoms. So this is C13H19O7, but P3. In compound D, the oxygen atoms have been replaced by sulfur atoms. So C13H19S7N3. What is the difference in the relative molecular masses of compound C and compound D? So pretty straightforward question. First, let's find the molar mass of compound C. So that's 13 times 12, because 12 carbons, plus 19 hydrogens, 7 oxygens, and 3 phosphoruses. So phosphorus, I believe, is 31. Yes, 31 for phosphorus. That's equal to 380. Very similar for compound D. But this time we have 7 sulfurs, which is 32.1, and the 3 nitrogens. And that's equal to 441.7. So the difference would just be to subtract both values, and that's 61.7. Then question 3 is about compounds and ions of iron 2 and iron 3 that contain ethane diarrhea ions. The ethane diarrhea ion shown below is an example of a bidentate ligand. Explain what is meant by the term bidentate ligand. So bidentate refers to the 2 lone pairs of electrons, and a ligand is just a species that can donate that lone pair of electrons to a central metal ion to form either, you could call it a dative covalent bond, or a coordinate covalent bond. Then for part 2, a complex ion E contains 3 ethane diarrhea ions bonded to iron 3 ion in an octahedral shape. Complex ion E exists as a mixture of 2 optical isomers. Draw 3D diagrams to show the structures of the optical isomers of E, include any overall charge. So 3 ethane diarrhea ions would be -6 in total, and iron 3 is just 3 plus. So if you add both of them together, the net charge of the complex ion would be 3 minus. Then for drawing 3D diagram, could start with iron in the middle and the 6 bonds that surround that. So the straight lines that you see, those indicate the bonds are on the plane of the paper. Dashed lines are the bonds that go behind the plane of the paper, and the wedged lines are the bonds that come off the plane of the paper towards you. Now, where you draw these lines are extremely important. The only correct way to do it is the way I have shown on the screen. If you do swap the lines around, there's a very high chance you can get it wrong. So just stick to this version of it. Then it's just a matter of filling in the ligands. We have a diagram, so that should make life slightly easier. So oxygens with the lone pairs would be closest to the iron, and then just everything else. Now, I have chosen to do the skeletal formula, ignoring the carbons. You could include the carbons. I don't think it really matters, as long as you have done it correctly. Again, please excuse my drawing. I know it's not the most accurate, but hopefully you can see the bonds. So square brackets and the overall charge on the outside. Then as for its enantiomer, or the optical isomer, well, if you find drawing this a bit confusing, a quick tip is to draw a line of symmetry down the middle so you can see the right and the left-hand side. So on this diagram, it looks like the right-hand side has 2 ethane diurate ions. Therefore, on its mirror image, or enantiomer, it should be the left-hand side that would have the 2 ions. So there you have the second enantiomer. Part B then is a student plans an investigation to find the numbers of waters of crystallization X in a sample of hydrated iron 2 ethane diurate. The student decides to carry out a redox titration between solutions of iron 2 ethane diurate and potassium manganate in acidic conditions. In the titration, both iron 2 ions and ethane diurate ions are oxidized. Construct half equations for the oxidation of iron 2 and ethane diurate ions. So half equations show the transfer of electrons, therefore these equations should have electrons. Starting with iron 2, that gets oxidized to iron 3+. So to balance charges, 1 electron is required on the right-hand side. So now both sides of the arrow have an overall charge of 2+. As for ethane diurate, this one is slightly more tricky if you're not familiar with their ions, but try to think about it a bit logically. What could carbon and oxygen give you? Go-to thing would have to be carbon dioxide, but I do fully understand that you may not be able to think of such things in an exam, especially if you're under a lot of pressure and stuff. So the only way around it is to do as many exam questions as you can, because that way you expose yourself to the different types of ions, and it's like less of a shock to you. Then as for balancing charge, it's just 2 electrons required on the right-hand side, so now both sides of the arrows have a charge of 2-. Part 2 is a student prepares 250 centimeter cube solution of iron 2 ethane diurate by dissolving 1.295 grams of it in dilute sulfuric acid. The student titrates 25 centimeter cube samples of this solution with 0.02 moles per decimeter cubed potassium manganate in the burette. The student carries out a trial followed by 3 further titrations. The diagrams show the initial burette readings and the final burette readings for the student's 3 further titrations. All burette readings are measured to the nearest 0.05 centimeters cubed. So that's the resolution that you're expected to use when you're filling in the table. So when you fill it in, all the values should be to 2 decimal places. So then part 3 is the uncertainty in each burette reading is plus minus 0.05 centimeters cubed. Calculate the percentage uncertainty for the titer in titration 1. So the formula that you can use for this is number of readings. So that's the number of readings that you take, multiplied by the uncertainty, divided by the final reading, or the final value. So as for the readings, because you're taking a final and an initial, that's 2 readings in total, times by the uncertainty, and the final value, the final reading, is the titer, so 21.65. Multiplied by 100, and that comes out to be 0.46%. Then question part 4 is, in the titration, 5 moles of iron 2 ethane diurate reacts with 3 moles of manganate ions. Analyze the student's results to find the numbers of waters of crystallization X in the hydrated iron 2 ethane diurate. So whenever you're asked to find waters of crystallization, that's usually the difference between the molar mass, or the MR, of the hydrated compound subtracted by the MR of the anhydrous compound, because that would tell you the molar mass of the water present in it. So we already technically have the anhydrous molar mass, because it's just this section that you could easily find using the periodic table, and that comes out to be 143.8 as the MR of the anhydrous salt, or compound. Right, so that means we'd have to use the information provided to find the MR of the hydrated compound in order to subtract both values. So looking back at the information provided, it looks like we have the concentration of manganate, and we also have its volume because we have the titer readings. So then the mean titer, which is between the concordant results, so from titers 1 and 3, mean titer would be 21.6. So then the moles of manganate ions is equal to its mean titer multiplied by its concentration, which was 0.02. So that comes out to be 4.32 times 10 to the minus 4 moles. Then for the moles of iron 2 plus, we have the ratio, which is 5 to 3. So that means the moles of iron would be 5/3 times the moles of manganate. And that's equal to 7.2 times 10 to the minus 4. But mind you, this would be in 25 centimeters cubed, because that's what the student did initially. So the total volume was 250, but they used 25 centimeter cube samples. That means we'd have to scale up to 250 by multiplying by 10. So then the original moles in 250 centimeters cubed would be 10 times that mole value. So 7.2 times 10 to the negative 3 moles. So then to find the MR of this compound, we could do the mass that was provided in the question as 1.295 divided by this mole value. And that's equal to 179.9. So this is the MR of the hydrated compound. We had the anhydrous MR as well. So if we subtract the two, that gives us 36. So the total MR for the water present is 36. To find out how many molecules are present, we can divide by 18, which is the molar mass of just one water, and that's equal to 2. So this means the compound would be FeC2O4.2H2O. Question 4 then is about chemistry of compounds containing phosphorus. Phosphorus forms several acids, including H3PO4 and H3PO3. H3PO4 is a tribasic acid. The equilibria for dissociations are shown below. During the equilibrium, H2PO4- behaves as both an acid and a base. Explain the statement using equilibria 1, 2, and 3 as required. So to answer this question, you're basically trying to find which equations define its acid behavior and its basic behavior. So where it behaves as an acid is the equations in which it can donate hydrogen ions in solution. So looking at all three, it looks like in equilibria 2, H2PO4- can release hydrogens in the forwards direction. So that would be in equilibria 2, it can donate hydrogen ions. Then as for it behaving like a base, this is when it accepts hydrogen ions. And looking at the equations, it looks to be equation 1 in the reverse direction. So H2PO4- can gain H plus to form H3PO4. So that is in equilibria 1, it can accept hydrogen ions. Part 2 then is in a H3PO3 molecule, the oxygen atoms are covalently bonded to the phosphorus atoms, the hydrogen atoms are bonded to the oxygen atoms. Draw the structure of H3PO3 showing all the bonds. On your diagram, include the values for the OPO bond and the POH bonds. So since we have only one phosphorus, we can stick that in the middle, and we know that all of the phosphoruses are bonded, the only phosphorus is bonded to oxygens, and in turn, the oxygens are bonded to hydrogens. Well, we can sort of actually slightly change that because we know that oxygen has 2 lone pairs. So this would give you like a bent angle type of shape thing. Right, and for the bottom as well, slightly bent. You don't have to show the lone pairs, I'm just showing it for the sake of explaining. Right, then as for the bond angles, well, around the oxygen, it looks a lot like a water molecule, which has the bent angle. That is about 104.5. Now, if you don't remember why it's 104.5, you can stick around for the explanation. You can skip ahead if you already know it. So technically, around that oxygen, there are 4 things. The 4 things are the 2 lone pairs and the 2 bonded pairs. So technically, something with 4 things around it should be tetrahedral, which is 109.5. But the presence of the 2 lone pairs will decrease that bond angle by 2.5. So we're subtracting 2 times 2.5, which gives you 104.5 as the bond angle, 104.5, yeah, as the bond angle. Then as for the OPO bond, which is this one, we'd have to figure out if there's any lone pairs on the phosphorus. So let's have a look. Click phosphorus, yep, group 5. So that means 3 bonding pairs and 1 lone pair. So again, technically 4 things around it, which should be 109.5, but the lone pair decreases that by 2.5 degrees, leaving us with 107 degrees as the bond angle around that. Part 3 is the systematic name of H3PO4 is phosphoric 5 acid. What is the systematic name of H3PO3? To answer this, we need to figure out the oxidation of phosphorus, and we can do that by figuring out or finding the oxidations of the elements surrounding it. So hydrogen is always +1, 3 hydrogens would be +3, oxygen always -2, 3 oxygens would make it -6. So over here, we'd have to have phosphorus with a +3 charge in order for all of this to equal to 0. Therefore, the name is phosphoric 3 acid. Part B then is phosphine, pH3, is a poisonous gas. Phosphine reacts with oxygen gas to form phosphorus 5 oxide and water. Write the equation for this reaction. So phosphorus 5 oxide is really P4O10. But let's say for some reason you had forgotten this or you did not know this, you could use a little trick to figure out what the compound would have been using oxidation numbers. We know that phosphorus is +5, and oxygen is always -2. The trick is to swap those numbers and bring them down. So if we swap the numbers, that becomes P2 and O5. Right, so that would have been the compound, which I know looks a lot different to P4O10, but both of them were correct. The main answer was this one, but it was also acceptable to say P2O5. So using that, the equation would be pH3, that reacts with oxygen to form P2O5 and water. Then for balancing it, we require a 2 to balance the phosphorus is there, a 3 to balance the hydrogens on both sides. Finally, for the oxygen, it's a 4 in front of the O2, so that each side has 8 oxygens. Part 2 is aqueous silver nitrate, AgNO3, is reduced by pH3. The unbalanced equation is shown below. Balance the equation and use oxidation numbers to explain why this is a redox reaction. So why oxidation and reduction are happening simultaneously. Now we know it says that silver is reduced, and we can also see that because it goes from +1 to 0. So that means silver here is gaining 1 electron. And that electron must have come from pH3. It would have to be the phosphorus because we know that the hydrogen here is always +1 in terms of oxidation. 3 hydrogens is a total of +3. That means phosphorus is -3. And it looks to be that phosphorus goes from -3 to +3 in this compound. We know that's +3 because we figured that out in a previous question. So that looks to be a loss of 6 electrons for phosphorus. So those 6 electrons are being gained by the silver. But the thing is, silver can only gain 1 electron. So in order to gain 6, well, there has to be 6 silvers present. I'm just going to erase the other numbers so they're less confusing. All right, there we go. So we know that silver is 6. Now that should make everything else quite easy to balance. So 6 NO3 is here, therefore we need a 6 over here. Then we can look at the hydrogens. So it looks like 6 here plus another 3 is 9. So to get 9 on this side, we have to add numbers. Now, do not touch the pH3, because if you add a number in front there, that means we'd have to balance the phosphoruses here, which, again, gets confusing. So do it with the water part. So to get 9 over here, if we included 3, that becomes 6 plus the other 3, so 9. As for the explanation, it's pretty much what I said already, that silver is the one getting reduced as it gains 1 electron, and pH3 is oxidized to +3 when it loses electrons. Right, question C is when phosphorus 5 chloride, PCl5, and ammonium chloride are heated together, the compound P3N3Cl6 is formed together with HCl gas. P3N3Cl6 has a cyclical structure like the Kikuli structure of benzene. Write the equation for the reaction of PCl5 and ammonium chloride to form P3N3Cl6. So that's PCl5 plus ammonium chloride, NH4Cl. That forms P3N3Cl6 and also HCl gas. So for balancing it, let's start with the phosphorus and the nitrogens. So we have 3 each on the right-hand side, so 3s on the left. Then we could do the chlorines, so that's 15 chlorines here, plus another 3 here, so 18. Now we already have 6, so we need 12 more. Then looking at the hydrogens, well, it's 12 over here as well, so that's pretty much balanced. Part 2 is to calculate the percentage by mass of phosphorus in the compound. So pretty straightforward. You could just use a datasheet to find the MRs, or the mass of each atom. So it's 31 from phosphorus, if I recall correctly, divided by the entire compound's MR, which is 348, times 100, and that's 26.7241%, which to 2 decimal places is 26.72. Part 3 then is to suggest one example of evidence that could show that this compound has a Kikuchi structure rather than the delocalized structure. So the Kikuchi structure has double and single bonds that are alternating, something like this. And if the bonds are alternating and localized in place, that means those areas where the double bonds are extremely dense, which would make the compound susceptible to electrophilic attack, right? So if it did have the Kikuchi structure, it would react with bromine water to decolorize it. So that's one piece of evidence. Another piece of evidence could be the fact that the bonds are different lengths, because we know that double bonds are shorter than single bonds. So just said that bonds are different lengths. Right, another piece of evidence could be the fact that hydrogenation would have been more exothermic than expected. Part 4 is in a molecule of P3N3Cl6, all of the N and Cl atoms are bonded to phosphorus atoms. Suggest a possible structure for a molecule of P3N3Cl6. So to meet this criteria, well, it can't be that nitrogen and chlorine are directly bonded because they're all bonded to phosphorus. So that tells us that we have phosphorus. It's bonded to nitrogen, but also bonded to chlorine. Okay, so perhaps we could alternate the nitrogens and the phosphoruses, right? And Kikuchi structure, so alternating double and single bonds in that case. So I guess we could just stick the chlorines around the phosphoruses. And that should make sense, right? And it also does make sense because phosphorus, being in group 5, has 5 electrons in the outer shell, and it's forming 5 bonds. Right, so that would be the answer. So now on to question 5, which is about the analysis of organic compounds. A student investigates the alkaline hydrolysis of 1-bromopropane as outlined below. In step 1, the student adds 1-bromopropane to an excess of aqueous potassium hydroxide in a pear-shaped flask. In step 2, a TLC chromatogram is run using propanol and the reaction mixture. The reaction mixture is refluxed, and a TLC chromatogram of the reaction mixture is run every 10 minutes in step 3. So here are the results. Now, what we can tell that's going on is when 1-bromopropane is hydrolyzed, it becomes propan-1-ol due to nucleophilic substitution. And we can see this on the results because a reaction mixture that would have contained the 1-bromopropane, that starts to decrease, but it is actually being converted into this dot, which is on the same level as propan-1-ol, so we can assume that the compound being produced is propan-1-ol. Okay, so the first question is to determine the RF value of propan-1-ol. So this is the distance moved by the substance divided by the distance moved by the solvent. So this would be up to the solvent front, which is a bit difficult to show here. But quite simply, you would have to measure the distance between the baseline to the middle of the dot. Just be careful that it is actually the middle of the dot, otherwise you may get it slightly off. And divide that by the distance from the baseline up to the solvent front. Part 2 is to write the equation for the alkaline hydrolysis of 1-bromopropane, show structures of the organic compounds. So propane being 3 carbons, 1 bromo, it's bromine at the carbon 1 position. That reacts with OH minus, and that's nucleophilic substitution. So OH replaces the bromine, and we have Br minus present as well. Right, so that's 1-bromopropane being converted into propan-1-ol. Part 3 is a student investigates the alkaline hydrolysis of 1-chloropropane using the same method as 1-bromopropane. Predict with reasons how the appearance of the reaction mixture in the chromatogram produced after 20 minutes would be different when 1-chloropropane is used instead of 1-bromopropane. Suggest why propan-1-ol is run alongside the reaction mixture. So I would say this part is pretty straightforward. We sort of touched on it earlier, that the propan-1-ol, it acts like a reference point to show us that the reaction mixture is being converted into propan-1-ol, right? So it's there to monitor the progress. Now, as for how it would be different with 1-chloropropane at 20 minutes, we'd have to think of the bonding. So we have the carbon-chlorine bond and the carbon-bromine bond. From AS chemistry, you should remember that the carbon-chlorine bond is a lot stronger, which would make that bond less reactive. So what you would see at 20 minutes is that the top dot present over here would actually be slightly bigger for the chloro compound than the bromo compound. Again, because this bond is quite difficult to break, so less of it would be converted into propene-1-ol. So then for part B, compounds F, G, H, and I are structural isomers. A student carries out test tube tests on the compounds. The student records the observations after carrying out each test. These are shown in Table 5.1. In Table 5.1, 2,4-dinitrophenolhydrazine has been abbreviated to 2,4-DNP. Write the formula of the species causing the colors after refluxing with acidified dichromate. So the green color, that is due to Cr3+. You should remember this from the transition metal chapter. And the orange solution, that is due to the dichromate. Then the orange solution, that is due to the dichromate, and that's Cr2O7 2-. Part 2 is the student is provided with further information about compounds F to I. They all have the molecular formula C5H10O, and one of the compounds is alicyclic, the other compounds are unbranched. Use this further information and the student's observations in Table 5.1 to answer the following. So that is, how do the observations provide evidence for the possible functional groups in compounds F to I, and suggest a possible structure for each of the compounds F to I? Show your reasoning. Right, so let's look back at the table. First, let's decipher what each test would tell you. So 2,4-DNP, this tests for carbonyl compounds. So you're looking to see either esters or even aldehydes, ketones, you name it. Acidified dichromate, this is typically for primary and secondary alcohols, but also to a certain degree aldehydes, because when aldehydes are oxidized into carboxylic acids, you could use acidified dichromate as the oxidizing agent, and you would also see the color change with that. So let's write that down. So also aldehydes. Bromine water, this is the carbon double bond. Tollens reagent, this is just for the aldehyde. So looking at compound F, with 2,4-DNP, the solution is orange, so not an orange precipitate, which should tell you there is no carbonyl, so it cannot be ketone or aldehyde. It is green with acidified dichromate, which means that the OH would have gotten oxidized, meaning either primary or secondary alcohol. Bromine water was colorless, which confirms the presence of a carbon double bond. Tollens is colorless, which means not an aldehyde. All right, compound G, orange solution again, so no carbonyl. Green solution, meaning there would have been primary, secondary alcohol, not the aldehyde, because if it were, you would have also had orange precipitate, but we don't. Orange solution, which means no carbon double bond, and tollens is colorless, again, not an aldehyde. Compound H has an orange precipitate, so that's good. That means either ketone or aldehyde. Orange solution, which tells you that this compound that had the carbonyl could not have been further oxidized, which proves that it is a ketone. We can further prove this with Tollens reagent, which is colorless, and confirms that it was not an aldehyde, but it is a ketone. So let's get that down. We know for a fact that's a ketone. Compound I, well, just based on the silver mirror, we know that this is for a fact an aldehyde. Okay, wonderful. So then it's a matter of drawing it all out. Let's do the easy ones first. So H and I. So that was 5 carbons, 10 hydrogens, and 1 oxygen. 5 carbons. Now, where you place that carbonyl group doesn't matter. You could have it in the middle or off to the side like this. Right, and then for the hydrogens, there's 10. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Great. Compound I. So that's the aldehyde. 5 carbons again. The corner carbon has the aldehyde group. Then hydrogen, so that's the first one. 2, 3, 4, 5, 6, 7, 8, 9, 10. Great. Then we've got F and G. Now, we were told that one of them is alicyclic, which means that whichever one is alicyclic is not the one that has the double bond. Because when a compound is alicyclic, there's less hydrogens, and also double bonds. Having double bonds would also reduce hydrogens. So you can't have both, because if you had both, there would be less than 10 hydrogens. So the one that does have the carbon double bond, meaning F, would not be cyclical, which tells us that G has to be the cyclical one. Right, so let's do F. We know that this is not cyclical, so straight chained. There is a double bond. You could stick that wherever. I'm just going to put it in the middle. The mark scheme has it either also on the first position, so that was fine. And as for the alcohol group, so we know either primary or secondary, can't confirm which one, so it doesn't matter, you could just stick it anywhere as well. Primary or secondary, both were correct on the mark scheme. Then for G, We know that this is cyclical, so 5 carbons, pentagon shaped, and an OH. I forgot the hydrogens here. There we go. Right, for this one, let's count the hydrogens. So that's 1. Second one would be here. 3, 4, 5, 6, 7, 8, 9, 10. Great, so that's it for the question. Now, when you're writing this out, you don't just get marks for the structures. You do need to have a logically explained reasoning for it. So try to use the bullet points for your reasoning. It helps clearly state that. And again, asterisk means quality of written communication. So just make sure your answer is not vague and as clear as possible. And I believe, yes, that is the last question. So if you stayed for so long in the video, thank you for watching. And if you found it useful, please do give it a like and subscribe.